So let's pick up where we left off at the end of the last video, talking about some measures of variability. The first one we'll talk about is just the range. And the range is a very simple and a fairly crude measurement. But all the range tells us is the high score versus the low score, or minus the low score. And the fancy way of calculating that, or the more accurate one, is the upper real limit maximum minus the lower real limit minimum. And you can read about that in your book. But it's basically the high versus the low, and then if you add 1 to that, it makes it a little bit more accurate. So that's the range. Again, kind of a crude measurement, but sometimes used just to get a picture of the spread of scores. The interquartile range is the same as the range, except that it throws out the extreme scores. So it's the third quadrant minus the first quadrant. So you take out the lowest 25% and the highest 25% and divide that by 2, and that's called the semi-interquartile range. The interquartile range is just the quartile 1 minus quartile 3. So we don't use that one very often, really at all in this class. What we'll concentrate most on is the standard deviation or the variance. And we'll spend some time looking at a standard deviation and variance and how those are useful for us. So if you'll look at the let's just look at these. Standard deviation is how deviation just means distance from the mean, like how far away from the mean is each person's score. So each person has a deviation score. So the standard deviation, which is this little Greek letter S, sigma, that is the average distance from the mean. So each person has a deviation score, or a score telling how far they are from the mean, and the average of those all together is the standard deviation. So it's really a pretty simple concept, although the calculation gets a little bit more complicated. Now the variance is just the standard deviation squared, and so you see this over here in the black, and it's just sigma squared. So sometimes we use the variance instead of the standard deviation. So how's this calculated? Well, the first step is to calculate the sum of the squared deviation scores. So in the sum of squares, the first one we have is what we call the definitional formula. And if you've got a very simple data set, this one is the easiest one to use. It's the sum of each person's score minus the mean. And for each one of those, you square them, and then you add them. You square each person's deviation score, and then you add them all together. Now, why do we have to square them? But the reason is because this is kind of a mathematical oddity. If you just take each person's score and subtract the mean from it, if you just add those all together, all the deviation scores, you'll always just get 0. So that's kind of a meaningless number. So we square each person's deviation score and then sum them together, and we don't get 0. The computational formula is probably a little bit easier to use, although it doesn't look simpler, but if you have a large data set, this one's probably easier. It is the sum of x squared minus the sum of x squared divided by n, and that's a big letter N, all the scores. So here you just have to differentiate between what is the sum of x squared, that is the sum of everyone's x score, and they've already been squared. And then the second unit over here is the sum of all the x scores put together, and then you square them. So that one is the computational formula. And so that is just how we calculate the sum of squares, and then to get the standard deviation, we use this last formula, and this is the formula for the population standard deviation, and it is the sum of squares divided by n, the number of people in that sample, and you take the square root of that. And of course the variance is just that same formula without the square root sign, because that's the standard deviation squared. And so I want us to notice what special thing we do if it's a sample standard deviation instead of a population one. We calculate the exact same way, but we put n minus 1 in the denominator instead of n. And the reason for that is, look at this little graph over to the right here. If you have a variability in a sample, and this is this bottom line down here, That's the variability in the sample. If you have the whole population instead of just a sample, the variability is likely to be more. It's almost surely going to be greater variability if you look at all the scores in a population versus just the scores in a sample. So that n minus 1 in the denominator is a way to kind of control for that and to make up for it. So here we see our normal curve, and we see the standard deviation, one standard deviation above the mean. And these percentages are important to remember. They always stay the same as long as the distribution is a normal distribution. Between 0 or the mean and one standard deviation above the mean will be 34.13% of the scores. And so if you want to double that and take the area between -1 and one standard deviation above the mean, that will be 68.26% of the scores, or roughly 2/3 of the scores is within this area, one standard deviation around the mean. If you go on up one more standard deviation above the mean to 2, the standard deviation of 2, we encompass another 13.59% of the scores, and of course we would do the same thing in this direction. So between -2 and 2 standard deviations around the mean, it's about 95% of the scores. I think it's 95.44%. And then if you go all the way out to 3 standard deviations above and below the mean, you're going to get about 99%, or virtually all of the scores. So that's the way that falls out. So let's look at how we use standard deviation in descriptive statistics. It helps us to describe the distribution. It helps us to know how spread out the scores are, or how close together they are in that distribution. If we have a mean of 40 and a standard deviation of 4, the scores are not too spread out. If we have a mean of 40 and a standard deviation of 8, we're going to show that the scores are quite a bit more spread out. It also helps us to interpret individual scores in that distribution. So a score of 42, and this one that we're looking at below here, a score of 42 is going to be just about half a standard deviation above the mean. So it's still fairly close to the mean. You're a little bit better than average, but not a lot better. An IQ of 110, if we know that the average IQ is 100, the mean IQ is 100, and if the standard deviation is 10, then we would know that our IQ is 1 standard deviation above the mean. A height of 80 inches, how much above the mean is that? We're pretty sure it's above the mean, but how much above the mean is it? So it helps us to know where we stand in the distribution, if we're above the mean or below the mean, and how much. So let's look at this little distribution of scores, and I want you to notice that in sample 1, the scores are pretty close together, 34, 35, 37, 35. Those don't have a whole lot of spread to them, so they will have a very small standard deviation, showing that they are not very spread out. This distribution is all pretty close together. Sample 2, 26, 10, 64, and 40, much more spread out, and these two have the same mean, but the spread is so much greater in sample 2. You have a lot more spread of scores there. So let's look at these two experiments just to show, why do we care about the standard deviation? What difference does it make? And when we move on to inferential statistics, which we will in the next few days, we will see how this comes into play. So in experiment A, we have sample 1 and sample 2, and as you can see, the scores are all pretty close together. They're pretty close. They're all just within a few of each other. And so it's pretty easy to look at that experiment and say, well, I believe sample 2 has a higher mean than sample 1, because you can just tell by looking at the scores. And the reason you can tell is because they're not spread out very much. In experiment B, the scores are much more spread out. And it's a lot harder to just glance at that data in experiment B and say that sample 2 has higher scores than sample 1. And the reason it's harder is because they're so spread out. So look at this sentence at the bottom. Low variability helps us to see clear patterns in the data. On the left, we have low variability, and the pattern is much clearer. So would you believe, and we're going to look at these graphs, this is the data on a graph, and would you believe that the mean difference is between sample 1 and sample 2 is 5 in both experiments. Sample 2 was 5 points higher than sample 1 on average. But in the data from experiment A, look how easy it is to see this. If you stack it in the little bar chart, it's so easy to recognize that. Down here, not so much. And again, it's just because the data is so much more spread out. So low variability helps us to see patterns in the data more clearly. And when we get into inferential statistics, that's going to become very important, because when we do a t-test or a z-test, or many of the analyses we'll be doing, we'll see that low standard deviations always help us. They are always a good thing. So let's look at in the literature and see how this would be reported. It's not always the same, but it's close to the same. So in this one, and it doesn't really matter what this experiment's about, but I'll tell you, it's about, boys and girls, like school-aged children, and whether types of cartoons they watch seem to be corresponding to different behaviors, like violent behaviors. So violent cartoons and the control are the regular cartoons with no violence in them. And so the kids watch the cartoon, and then they observe their amount of violent behaviors maybe on the playground. So it doesn't really matter what the data is about, but what I'm really putting this here to show you is, this is from your textbook. How is this reported in the data? So this is just an APA friendly or compliant chart that shows, or table that shows the data. Males and females are in the rows, and the violent and control are in the columns, and it reports both the mean and the standard deviation. And sometimes you'll see them reported as mean plus or minus standard deviation. That's a little bit less space that it takes up. So sometimes you'll see it reported that way. But that would be like in a journal article when you see the means and standard deviations reported. So that is all we're going to talk about for variability, and the textbook is very friendly toward you gaining a little bit more confidence with these concepts. So read your textbook, and we'll talk more and proceed from there in Chapter 5 with z-scores.